All right, let's really dig into something mind-blowing today. Imagine materials so impossibly thin, they're just a single layer of atoms. But here's the kicker. Not just any single layer one that's completely jumbled and disordered at the atomic level, yet still incredibly powerful and useful. This isn't science fiction. It's a groundbreaking new breakthrough that scientists are calling atom-thin amorphous metal chalcogenides. I know it's a bit of a mouthful, but trust me, the science behind it is truly fascinating.
It really is.
Our source for this deep dive is a recent incredible article published in Nature Materials, which details this scientific feat. Our mission today is to take this complex, cutting-edge research and distill it into clear, exciting insights. We want to show you exactly why it matters for everything from the electronics in your pocket to how we might produce clean energy in the future. We're basically going to help you understand the magic behind making the unmakeable.
And what's truly fascinating here, I think, is how this research elegantly tackles a fundamental challenge. Something that has puzzled material scientists for decades, really. It's not just about making something small, though that's part of it. It's about making something small differently, in a way we previously thought was, maybe impossible. And that difference, that different approach, it opens up a whole new universe of possibilities.
Differently. Okay. How so?
Well, for so long, the prevailing wisdom in creating advanced materials has been all about achieving perfect, ordered structures, what we call crystalline materials. We've always chased perfection and order, thinking they lead to the most predictable and desirable properties.
Right, like stacking Lego bricks perfectly.
Exactly. But this work, it's a paradigm shift. The breakthrough lies in deliberately embracing disorder, or amorphousness at the atomic scale, and doing so in a way that creates entirely new, powerful functionalities. It's like finding a hidden superpower in chaos, intentionally creating that chaos.
Finding a superpower in chaos. I like that. That's a powerful way to put it. So let's start with the basics then, because understanding these core concepts is definitely key to grasping the breakthrough. When we think about materials at a fundamental level, most people probably picture those neat, ordered structures you mentioned.
Crystalline.
Crystalline, right, like tiny Lego bricks stacked perfectly, layer upon layer, in a precise, repeating pattern. A diamond is a perfect example, isn't it? Its carbon atoms are arranged in a very specific, repeating crystal lattice that makes it incredibly strong and predictable. Metals like copper or aluminum, too, they're crystalline.
That's a standard picture, yes. Neat, repeating patterns.
But what if those Lego bricks were just scattered, randomly connected, jumbled up without any discernible long-range order? Imagine a pile of tangled string rather than a neatly coiled rope.
That's a great analogy. That's much closer to what we mean by an amorphous material.
Okay, so amorphous is jumbled, like glass. Is common glass amorphous?
Exactly. Glass is a classic example. It's a solid, but its silicon dioxide atoms are arranged randomly, almost like a frozen liquid. Or even many plastics, like, say, the bottle your water might be in. They're solid, but their molecular structures are chaotic and disordered. And these amorphous materials often behave very differently from their crystalline cousins, precisely because of that internal jumble.
Right, different structure, different properties, makes sense. Now let's add another layer of complexity here. We're not just talking about amorphous materials in general, but specifically atom-thin or single-layer limit materials. This means films that are so incredibly thin, they're just a single atomic layer thick.
Almost unimaginably thin.
Yeah, we're talking about dimensions often around 1 nanometer. And just to give you some perspective, a human hair is about 80,000 nanometers thick.
80,000. It's 1 to 1.
Right. An average strand of DNA is maybe 2.5 nanometers wide. Even a tiny virus is, 30 nanometers? So when we say atom thin, we are literally talking about something just a handful of atoms stacked vertically, if that. It's a scale that just pushes the very limits of what we can create.
That's exactly the challenge, and this is where the fundamental problem really kicks in, because most atom-thin materials that we've successfully created and studied so far, like the famous graphene
graphene.
or molybdenum disulfide, they're what we call layered materials. They naturally form in these neat stacked sheets, almost like pages in a book.
Okay, so they like being in layers.
Precisely, which makes them relatively easy to work with using traditional top-down methods. Like in the early days of graphene research, scientists literally used sticky tape.
Scotch tape, right. I remember reading about that.
Yeah, to peel off single layers from a larger chunk of graphite. That's called mechanical exfoliation. It's like peeling off a piece of adhesive tape from a roll. It comes off in a flat, thin sheet because it's already layered.
Okay, that works for layered stuff. But here's the rub, as they say. Amorphous materials, by their very nature, don't form in layers. Their bulk forms aren't layered.
Correct. You can't just peel them off like graphene.
So the original research points out that their thermodynamically favorable grains are neither two-dimensional nor layered. Now, to break that down simply for you, our listeners, this means that these atoms inherently prefer to clump up. They want to form three-dimensional islands, or lumps, rather than spreading out into a flat, thin sheet.
It's their lowest energy state, their most comfortable configuration.
It's like trying to get, wet sand to form a perfectly flat sheet instead of little piles.
That's a good way to think about it. It naturally wants to form a dune, or a small hill, not a flat expanse. So the challenge isn't just making something thin, it's making something thin when all the natural forces, the very inclination of the atoms, are pushing against it, trying to make it lumpy. That's a huge hurdle. You've absolutely hit on the core difficulty there. If we connect this to the bigger picture, these materials are, as you said, energetically prone to forming these lumps. Scientifically, this tendency is often called the island growth mode, or more technically, Stransky-Krastenov growth.
Island growth, okay?
And that's the opposite of the desired 2D film growth, or Frank van der Merwe mode, which is where material spreads out uniformly, nice and flat.
So why? Why do amorphous materials prefer this lumpy island state?
Well, it comes down to their surfaces. They have what are called unpassivated surfaces with dangling bonds. Think of atoms as having tiny hands. In amorphous materials, many of these hands on the surface are just dangling freely, unconnected to other atoms in a stable, ordered way. They're like little magnets, almost desperately wanting to grab onto other atoms to complete their connections. And that naturally makes them clump up into those lumps or islands. That's their most comfortable, lowest energy state. So forcing them into a flat single layer means overcoming this really fundamental atomic inclination.
Okay, so if nature wants them to be lumpy, and their atoms are essentially, like you said, desperate to clump, how on earth do you manage to force them into a perfectly flat, single atomic layer? That sounds almost impossible.
It absolutely does, and that's precisely the ingenuity of this work. The challenge here is activating what's called a non-equilibrium kinetics process.
Non-equilibrium kinetics.
Yep.
Okay, what does that mean in plain English?
It essentially means you have to force the material to do something it doesn't naturally want to do. You do that by carefully controlling the process, the kinetics, how fast things happen, and the pathway they take, rather than simply relying on its natural, most stable energetic preference, which is its thermodynamics.
So you're controlling the journey, not just letting it settle into its preferred destination.
Exactly. And the why this matters is crucial, because amorphous structures possess truly unique characteristics precisely because of their lack of long-range order. Those uncoordinated surface atoms we talked about earlier, those dangling hands, they actually become highly active sites, giving these materials distinct properties that their crystalline counterparts simply don't have.
Like what kind of distinct properties are we talking about?
Well, our sources highlight some pretty striking examples. Take crystalline graphene, famously conductive, right? It's semi-metallic.
Right, conducts electricity very well.
But its amorphous counterpart, monolayer amorphous carbon, is actually an electrical insulator.
Wow, completely opposite.
Completely different behavior just from the arrangement of atoms. Similarly, amorphous boron nitride layers have lower relative dielectric constants than crystalline layers. What does that mean for you? Well, it makes them highly promising for semiconductor devices where you want to store less electrical energy or maybe improve signal isolation. So creating these atom-thin amorphous materials isn't just a scientific curiosity, it's a pathway to entirely new functionalities and maybe next-generation technologies.
Okay, so the payoff is potentially huge.
Yeah.
Which brings us back to the how. Given all those challenges, the clumping tendency, the thinness issue, the need for disorder, how did they possibly convince these materials to lie flat? What was the ingenious breakthrough? Here's where it gets really interesting, folks.
Okay, so the researchers found a surprising, almost counterintuitive helper: tiny, tiny liquid droplets of metal. And when I say tiny, I mean less than 2 nanometers across.
Less than 2 nanometers. That's incredibly small. Hard to even picture.
It is. Remember, your hair is 80,000 nanometers thick. So these droplets are almost at the scale of individual atoms. And this is the core of their nanodroplet-driven nanoribbon-to-film strategy. Imagine these metal clusters, specifically platinum in their initial work, when heated to a very precise and surprisingly low temperature for metals, just 120 degrees Celsius.
120 C, that's barely more than boiling water. For platinum.
Exactly. It's remarkably low for a metal like platinum.
Yeah.
At that temperature, these tiny clusters actually become liquid droplets. And these tiny liquid guides then essentially orchestrate the growth of the atom-thin film. It's truly ingenious, like using a microscopic squeegee, as you said earlier, to spread out a layer of material.
A microscopic squeegee. I love that image. So how did they even figure out that these tiny sub-2-nanometer droplets were the secret sauce? They didn't just guess, right? They must have run some experiments.
Oh, absolutely. They conducted a series of really elegant proof-of-concept experiments to truly understand the mechanisms at play. In their first experiment, which was basically a crucial control group, they deliberately deposited larger platinum nanoparticles. These were bigger, with diameters ranging from 2 to 6 nanometers onto their substrate.
Okay, so bigger than the magic 2-nanometer threshold.
Right. And when these larger particles were exposed to selenium vapor, that's the selenidation process, where selenium atoms bond with the metal. What happened? They grew into larger platinum selenide nanoparticles, just lumps.
Lumps. The island growth mode again.
Exactly. It clearly confirmed the dreaded island growth mode, the material clumped up, just as thermodynamics would predict. You can visualize it like dropping large beads of water onto a waxed surface. They just form distinct round beads instead of spreading out flat. So this showed them what not to do and confirmed that inherent challenge.
So the larger particles behaved exactly as expected clumping. Must have been a bit disheartening. But then they tried something fundamentally different, didn't they?
Precisely. For their breakthrough experiment, they used much, much smaller platinum atom clusters, ranging from a minuscule 0.3 nanometers up to that critical 2-nanometer size. And crucially, when these incredibly small clusters were heated to that specific low temperature of 120 degrees Celsius,
They liquefied.
they liquefied into those tiny droplets, and then something truly remarkable and unexpected happened. These droplets began to guide the growth of what they described as tadpole-like single-layer nanoribbons.
Tadpole-like. Like a head and a tail.
Exactly. Imagine a microscopic, almost invisible slug, or maybe a tiny, nearly atomic-sized tadpole, leaving a perfectly flat, single-layer trail behind it as it moves across the surface. That's essentially what they observed. Long, thin strips of material, just one atom thick, with a tiny liquid droplet perched right at the head, pushing the growth forward.
Wow. So the droplet is the head and the ribbon is the tail.
That's the picture. And the observation of these unique tadpole shapes, so distinct from just random clumping, was the definitive visual proof. It showed that these tiny liquid droplets were doing something entirely new, driving this 2D growth. It was their aha moment.
That tadpole analogy really clicks. So the inference here was clear. These atomic metal clusters were indeed liquefying into tiny droplets, and these droplets were the active agents driving the 2D growth, stopping the clumping. This must have been the crucial insight.
It absolutely was. The experiment showed definitively that the initial size of the metal cluster and its ability to liquefy into a droplet at that specific low temperature was the game changer. It transformed an inherent clumping behavior into a controlled spreading. And then an even more exciting observation emerged. They realized that if you had a high density of these tadpole nanoribbons—
Lots of tadpoles swimming around.
Exactly. They could actually merge together, stitching themselves into a larger sheet. This led them to hypothesize, and I'm quoting loosely here, that combining these distinct phenomena, reducing the metal source's size to an atomic scale, would result in a nanodroplet-driven 2D growth, which can be potentially used to grow an amorphous film at a single layer. This was the conceptual leap, the theoretical bridge, that paved the way for them to try larger-scale synthesis, to go from individual ribbons to a full, continuous film.
Okay, so they cracked the tadpole code, they understood the role of these tiny liquid guides. The next logical step was, naturally, to go big, or rather, to go wide, to create a complete film on a wafer scale, something practical for actual manufacturing, right?
Exactly, the ultimate test.
And they succeeded. They actually did it. They successfully grew a 1-nanometer thick amorphous platinum selenide film, PdSex, on a standard silicon wafer, specifically a silicon dioxide on silicon substrate covering a centimetre-scale area. They even specify a 1-inch amorphous film. That's a truly remarkable leap from seeing tiny ribbons to making a usable sheet.
It's a massive scale-up. And this brings us back to that crucial temperature, 120 degrees Celsius. As we discussed, this wasn't arbitrary. It was meticulously chosen and is absolutely fundamental to the whole thing.
Right, you said there are two key reasons.
Two key reasons. First, this temperature enables the liquefaction of those atomic nanoclusters. This is because of that principle called the Gibbs-Thompson effect, which, Simply put, just means the smaller something is, the lower its melting point can be.
Like a tiny ice cube melting faster than an iceberg.
Precisely. The surface energy dynamics are different at the nanoscale. So these incredibly tiny sub-2-nanometer platinum clusters melt at just 120 degrees Celsius. Compare that to bulk platinum, which needs over 1,700 degrees Celsius to melt. It's a huge difference. This is what creates those essential liquid droplets that then guide the growth.
So the tiny size basically supercharges its ability to melt at a much lower temperature.
That's wild. It is. And the second reason 120 degrees Celsius is so crucial is that lower temperatures naturally favor the formation of amorphous structures. Remember, amorphous means jumbled and disordered. If they used higher temperatures, the atoms would have too much energy, too much time to move around, and they'd arrange themselves into a perfect, ordered, crystalline structure.
Which is exactly what they didn't want for this specific material.
Exactly. They wanted the disorder. So the low temperature is critical for maintaining that desired amorphous state. It's a really delicate balance.
Okay, so they had the right temperature, the right size of middle clusters, the right conditions. They get these atom-thin amorphous films. But how did they confirm, beyond a shadow of a doubt, that what they grew was actually a uniform, single-layer amorphous film? And not just, some other weird, thin, maybe crystalline structure.
Right. Proof is essential. They used a whole battery of incredibly sophisticated characterization techniques. Each gave them a piece of the puzzle. For initial visual confirmation and to measure the thickness, they used standard optical images and something called atomic force microscopy, or AFM.
AFM, right? That scans the surface.
Yeah, it uses an incredibly tiny, sharp probe that scans the surface, mapping its topography at the nanoscale, like feeling the bumps. This clearly showed a uniform 1 nanometer thickness and a remarkably smooth surface. So flat, continuous film confirmed. Then, to confirm the chemical makeup, was it really platinum and selenium everywhere? They used energy-dispersive X-ray spectroscopy, EDS. That showed a uniform distribution of both elements across the entire film. Not patchy, nice and consistent.
Okay, thickness, smoothness, composition, checked. But the really important part, proving it was truly amorphous, not crystalline. How did they nail that down?
That's the million-dollar question, isn't it? For that, they used a technique called selected area electron diffraction, or SAED patterns. Imagine shining a beam of electrons through the material and seeing how they scatter. If a material is crystalline, with its neat repeating pattern, you'd see sharp, distinct spots in the diffraction pattern, like a fingerprint of its order.
A crystal fingerprint.
Exactly. But with these films, they observed something totally different. A diffuse halo without diffraction spots. This diffuse halo is the unmistakable fingerprint of an amorphous material. It means there's no long-range atomic order. The atoms are just jumbled.
The jumbled fingerprint.
Pretty much. And furthermore, they use atomic resolution HATE-ADF STEM imaging. That's high-angle annular dark field scanning transmission electron microscopy.
Okay, that's another mouthful. What does that do?
It essentially lets you see individual atoms, or at least columns of atoms, and the images directly showed no long-range order in the atomic arrangement. It visually confirmed the jumbled, disordered state at the atomic level. So all these results together strongly indicated, yes, they successfully synthesized a 1 nanometer thick amorphous PdSex film at this super low temperature. And as the researchers state, to the best of their knowledge, this is the first example of the CVD growth of amorphous metal chalcogenides approaching the single layer limit. It's really pioneering stuff.
That's genuinely groundbreaking science. It sounds like they not only did something previously thought impossible, but they also meticulously proved it every step of the way. But the how here, the kinetic growth mechanism, that still fascinates me. We know the tiny liquid droplets guide the growth, but why do they consistently stay at the very edge? Why don't they just get pushed up on top, leading to 3D growth? And how do those individual padpole ribbons actually merge into a seamless film?
Ah, right. This is where the why and how truly shine, and it really shows the elegant control they achieved. To answer your first question, why do the droplets stay at the edge? The researchers turned to incredibly sophisticated simulations. They used density functional theory, or DFT, calculations.
DFT, that's like a virtual chemistry lab.
Yeah.
Simulating atoms.
Exactly. It lets scientists simulate how individual atoms and electrons interact at a fundamental level, revealing their energetic preferences. And these simulations revealed something crucial. The platinum droplets have better wettability on the growing PdSex material than they do on the bare substrate underneath.
Better wettability. meaning they like sticking to the new material more.
Precisely. Think of a drop of water, it spreads out more easily on a surface it likes, high wettability, versus beating up on one it doesn't. The platinum droplet essentially prefers to stick to the newly formed PdSex material. And here's the crucial part. A platinum droplet below that critical size, around 2 nanometers, tends to stay at PdSex steps to maximally reduce the exposed surface area and surface energy.
Okay, what does that mean, staying at the steps?
Imagine the edge of the growing film as a tiny step up from the bare substrate. The tiny droplet finds it energetically favorable to sit right at that step edge. Think of a tiny ball on a slightly sloped roof again. If it's small enough, it wants to sit right at the edge where the roof meets the wall. That's the most stable spot, lowest energy. A larger ball might just roll right off onto the flat roof, or in this case, climb onto the new material layer. So this preference for the step edge is key to why these minuscule droplets guide the 2D growth, staying at the leading edge instead of climbing on top and starting unwanted 3D islands. They're sort of trapped at the growing front.
So the droplet finds its sweet spot right at the growing edge because of its size and its stickiness preference? Okay. But what about its motion? Does it just sit there, or does it actively move along, like a little plow pushing forward?
It absolutely actively moves. They describe it as a kind of controlled dance. They used another type of computer modeling, phase field simulations, which showed the platinum droplet moves along with the PdSex growth front. It's driven by that energetic preference of staying at the PdSex steps. Essentially, the new material forming behind the droplet continuously pushes the liquid droplet forward as it grows.
Ah, so the growth itself pushes the droplet.
Yes, maintaining that crucial edge position. But the simulations also revealed something interesting about the path. It can't be kept perfectly straight because Brownian motion randomly pushes the droplet off its track.
Brownian motion, that's the random jiggling of tiny particles, right?
Exactly, just the random jostling from atoms hitting it. Imagine a tiny ping pong ball being bumped randomly by invisible air molecules. This explains why the films don't grow in perfectly straight lines, but rather in those slightly wiggly, tadpole-like single-layer nanoribbon shapes we talked about. The critical point here, though, is that the growth of each ribbon stops when the platinum feedstock within the droplet is consumed.
So it runs out of fuel.
Kind of, yeah. This prevents it from growing wider or piling up into a 3D island. It's a self-limiting process for each tadpole. Conversely, if the droplet is larger than that critical 2 nanometer size, it has enough material and energy to climb on top, and then you get those unwanted 3D islands. Size matters.
Size definitely matters here. So, okay, that explains one tadpole. But it's not just about one droplet behaving, right? How do they all work together? How does that collective action happen to create a continuous film without gaps?
Exactly. That's the collective action part that solves the puzzle of getting a wafer-scale film. The simulations also showed how multiple droplets interact. This is really cool. When two tadpole growth fronts intersect, imagine two of those slug trails meeting, the droplets perform a fascinating U-turn.
A U-turn?
Yeah. They turn around to stay at the step edge of the uncovered substrate. They actively avoid climbing over the newly formed single layer next to them, because climbing over would lead to multilayer growth, which they want to prevent. This behavior effectively avoids climbing above the grown PdSex single layer and prevents multilayer growth, ensuring it stays just one atom thick.
Wow, they're like polite little builders avoiding stepping on each other's work.
Something like that. And with a high enough density of these droplets, they are basically spatially confined on uncovered substrate surfaces. They keep working until the substrate is fully covered by that first layer, ensuring a pure 2D growth mode. It's like a microscopic army of pavers ensuring every last bit of the ground is covered before stopping. And here's something even more amazing they saw. A self-healing process of tiny holes within the amorphous film.
Self-healing, what does that mean?
It means small gaps or pinholes that might initially form can spontaneously close up as the film continues to grow nearby, possibly due to atoms diffusing along the edges. It helps ensure a pristine, continuous final sheet.
That's incredible. A self-healing material at the atomic scale. It's almost like it fixes its own mistakes. So really, this entire process is, as you called it, a non-equilibrium kinetic growth mechanism. You're essentially controlling the process, the kinetics, to overcome the material's natural tendency, its thermodynamics. It's a very clever way of bending the rules of nature.
Precisely. And they also dug into the specifics of the reaction happening right inside the droplet at that low temperature. Because of the reduced melting point, the platinum is liquid. But the selenium vapor in the environment is relatively scarce. This creates what they call a SEEP-poor, selenium-poor, local reaction environment within the tiny droplet.
Not much selenium around.
Right. And this combination leads to supercooling. The liquid metal is below its normal freezing point, yet it stays liquid. This supercooling state causes a substantial increase in the chemical potential of PdSe. You can think of that as significantly increasing the platinum's eagerness or driving force to bond with whatever selenium is available. It really accelerates the PCC bonding.
Okay, so it speeds up the reaction. But how does that keep it amorphous?
Here's the final piece of the puzzle for amorphousness. At this remarkably low temperature, structural reconstruction, critical for defects annealing, is suppressed. What does that mean? It means the atoms simply don't have enough energy or enough time to rearrange themselves into a perfect, ordered, crystalline structure. Forming a crystal involves annealing out defects, letting atoms shift around to find that lowest energy, perfectly ordered state. But at 120C, that process is suppressed. It's too sluggish. This actively prevents crystallization and forces the material to remain in the desired defective, disordered, amorphous state. It's a very clever, multi-layered strategy.
Wow. Okay, so it's the droplet size, the wettability, the low temperature, the supercooling, the suppression of ordering. It all has to work together perfectly. So this incredible technique, this nanodroplet-driven strategy, clearly works beautifully for platinum selenide PdSex. But what if you need other materials? Different metals for different applications? Could they generalize this breakthrough? Or was it just a one-off trick for platinum?
That's a hugely important question, right? Is it a general method? And the answer is a resounding yes. And this is a critical finding because it shows the versatility and broad applicability of their method. The strategy was successfully applied to a whole family of amorphous noble metal selenides, or NMSs.
A whole family? Like what?
Well, not just PdSex, that's platinum selenide, but also RhSex, PdSex, and RhSex. So that's iridium selenide, palladium selenide, and rhodium selenide, respectively. These are all different noble metals, each with its own unique potential properties. And the fact that the same core method worked for all of them is really significant.
How do they make the others? Same process.
Pretty much the same core idea. They use something called ultraviolet photochemical reduction first to get the initial tiny metal nanoclusters. You can imagine using UV light to help break down precursor chemicals and form these incredibly small metal particles on a different substrate, molybdenum disulfide, MOS2 in this case. And then they applied the same precise low-temperature selenidation process with the nanodroplets. And the results were consistent across these different noble metals, all formed uniform, single-layer amorphous films. They verified this with multiple characterization techniques, just like with the platinum. It really confirms the robustness and versatility of the strategy. It's not just a single discovery. It looks like a general pathway, a blueprint for creating an entire new class of previously unmakeable material.
That's a genuine game changer, then a whole new family of materials unlocked. Okay, let's get to the payoff. We've hinted at it, but why go through all this intricate trouble? What unique properties do these atom-thin amorphous materials possess that make them so valuable for us, in the real world?
Right, the so what question. This is where the true power of this controlled disorder really starts to shine. One of the most significant findings is their tunable conductivity.
Tunable conductivity, you mentioned that briefly. How does that work?
Well, unlike most crystalline materials, which tend to have a fixed electrical conductivity based on their structure, these amorphous films have what's called degree of disorder, DOD, tunable conductivity. What this means for you is that scientists can actually change how well the material conducts electricity simply by varying its level of internal jumbledness, its disorder.
How do they vary the disorder?
They achieved this by annealing the films, that's essentially heating them gently to different temperatures after they were formed. This allows the atoms to rearrange slightly, changing the degree of disorder.
So they can literally dial in the conductivity, maybe like using a dimmer switch for electricity flow, just by tweaking the atomic jumble with heat.
Precisely. That's a great way to put it. And what's really fascinating is how it changed. The sheet conductance, how well electricity flows across the thin film, didn't just go steadily up or down as they heated it. It first decreased, and then it increased with annealing temperature, reaching a minimum conductivity, the worst conductivity, at around 300 degrees Celsius.
That's weird. It gets worse than better. Why?
It is unusual behavior, and it correlates directly with something called the density of states, DOS, at the Fermi level. Now, to put that simply, imagine electrons needing specific energy levels to be available for them to conduct electricity. The DOS at the Fermi level is a measure of how many of those immediately available slots there are. So this strange conductivity behavior is tied to how the number of available electron states changes as the disorder changes with annealing.
Okay, so the number of available lanes for electrons changes in a complex way.
Exactly. And this phenomenon is actually analogous to what's seen in electrical studies of amorphous monolayer carbon. It suggests a possible hopping conductivity model. Yeah, instead of electrons flowing freely like water in a wide pipe, like in a good metal crystal, in these jumbled materials, electrons might be hopping between localized states or spots within the material, like someone trying to cross a rocky river by jumping carefully from one stone to the next. The efficiency of this hopping changes with the disorder.
Interesting. So depending on the disorder, it can conduct better or worse.
Right. And get this. The pure amorphous film, the most disordered state as grown, surprisingly showed metallic behavior. It conducted electricity pretty well, but the film annealed at 300 degrees Celsius, where conductivity was lowest, showed slight p-type conductance modulation. That means it started behaving a bit like a semiconductor, specifically one where positive charge carriers dominate, which is really useful for building transistors. So yes, they can tune it from behaving like a metal to behaving more like a semiconductor just by tweaking their disorder with heat. That opens up a huge array of possibilities for tailoring materials for specific electronic functions.
That's a massive amount of control, switching between metal-like and semiconductor-like. How does this translate into a concrete, real-world application for electronics then? Did they test it?
They did. One immediate and incredibly promising application they explored was using these amorphous materials as high-performance hole injection contacts in p-type transistors. Okay, so imagine a transistor as a tiny switch controlling electricity flow. For it to work efficiently, it needs good on-ramps and off-ramps for the charge carriers. Those are the contacts. They need to efficiently get charge carriers, either electrons or holes, which are basically positive charge vacancies, into the active part of the transistor.
Okay, efficient on-ramps.
Exactly.
Yeah.
They tested the amorphous PdSex as a contact material for a tungsten diselenide WSE2 field effect transistor, or FET. WSE2 is a common material for these new 2D transistors, and they compared it directly with a standard graphene contact, which is often considered a good benchmark.
And what did they find? How did the amorphous stuff stack up?
The results were quite compelling, actually. The PdSex contact achieved p-type dominated FET behavior, meaning it was very efficient at injecting holes, those positive charge carriers, into the transistor. And the key metric, the saturation hole current, they could get through the transistor using the PdSex contact.
Yeah.
It was 2 orders of magnitude larger than with the comparison graphene contact.
2 orders of magnitude. That's 100 times larger.
100 times more current, yes. It means the amorphous PdSex was incredibly efficient at delivering those positive charge carriers into the transistor. This makes it a potentially powerful and efficient component for next-generation electronics, possibly leading to faster and more energy-efficient devices like processors or memory chips.
Wow, 100 times better contact efficiency. That's enormous. And I imagine that low growth temperature, that 120 degrees Celsius breakthrough we keep mentioning, that's also a massive deal for actually making these advanced electronics, right?
It is absolutely critical. That low growth temperature, 120 to 150 degrees Celsius, is compatible with the back end of line process, or BEOL. That's a hugely important term in semiconductor manufacturing. BEOL refers to the later stages of chip fabrication, where you build the interconnects and add other layers after the main sensitive transistors are already formed underneath.
So you can add these new materials on top without frying what's already there.
Precisely. This is especially vital for something called monolithic three-dimensional integration schemes. That's where you stack microchip layers directly on top of each other, creating much denser and more powerful circuits. If you try to add new layers using high temperatures, you risk damaging the delicate, already built layers beneath. But keeping the temperature so low, well below the typical 400 degrees Celsius limit for BEOL, means these new amorphous contact materials can be integrated without harming the complex structures already in place. This gives manufacturers immense flexibility and is a massive advantage for building the next generation of stacked, high-performance microchips.
Okay, so better contacts, manufacturing compatibility. That's huge for electronics. Did they discover any other superpowers that these unique amorphous materials might possess? Any other applications jump out?
They certainly did. Another really exciting area they investigated was electrocatalytic activity for hydrogen production.
Hydrogen production, like for clean fuel.
Exactly. Electrocatalysis here refers to how efficiently a material can act as a catalyst, a helper substance, in the process of splitting water, H2O, into hydrogen gas, H2, and oxygen using electricity. Hydrogen gas is a clean, renewable fuel. They compared their new amorphous samples with crystalline ones. They could get crystalline samples simply by annealing or heating the amorphous layers to make them ordered. Now, for traditional crystalline catalysts in this family, like crystalline PdSex, it's well known that only the edges of the material are highly active for this hydrogen evolution reaction, or HR.
So, again, only the boundaries, the very edges of the crystalline material are doing the work. The flat surface isn't very active?
Exactly. The flat basal plane is pretty inert. But, impressively, as the paper puts it, the amorphous samples demonstrated remarkably improved the hydrogen evolution reaction, HER, performance on both edges and the basal plane.
Both. So the flat parts are active too now.
Yes. This means the entire film, the whole surface of the amorphous material, is active for hydrogen production, not just the edges. This is a profound difference. It dramatically increases the available active area for the reaction, and it's a potential game changer for efficiently generating clean hydrogen fuel.
How good was the performance?
Their measurements showed its performance was comparable with PT. That's pure platinum metal, which is currently the gold standard, the best but also very expensive catalyst for hydrogen production. And it was superior to other transition metal dichalcogenide catalysts, which are another class of materials being explored for this. This result indicates a high activity of what they call intrinsic amorphous sites.
Intrinsic amorphous sites, meaning the jumbled up atoms themselves are the active spots.
That's the idea. Those jumbled atoms, those disordered arrangements, those dangling bonds we talked about earlier maybe, they are inherently active catalytic sites. This means the whole film contributes effectively to hydrogen production, making it potentially incredibly efficient for large-scale clean energy applications. It's a really huge step towards making hydrogen a more accessible and affordable fuel source.
That is truly exciting on so many fronts. Okay, let's try and wrap our heads around the big picture here. So what does this all mean for us? We've seen how cleverly manipulating tiny liquid droplets at precise, surprisingly low temperatures allow scientists to create entirely new forms of materials. Atom-thin films that are deliberately, controllably disordered or amorphous.
Right. It's not just about making things smaller, it's about making them fundamentally different at the atomic level.
And that difference unlocks properties that perfectly ordered crystalline materials simply don't have. We've explored the significant challenges, how these non-layered materials naturally want to clump up, and how hard it is to make them flat and thin. And we saw how this ingenious nanodroplet-driven strategy overcomes those fundamental thermodynamic hurdles, essentially bending nature's rules through kinetics.
Controlling the process, not just the outcome.
Exactly. And the implications look huge, from enabling faster, more efficient electronics with vastly better transistor contacts that are compatible with the next generation manufacturing techniques like 3D chip stacking, all the way to a significant leap forward in efficiently producing clean hydrogen fuel using the entire surface of the material. It's really a testament to how thinking differently about material design, embracing imperfection, in a way can lead to breakthroughs that could affect our everyday lives and the future of clean energy.
Absolutely. And looking ahead, this work isn't just about platinum selenide or even just noble metal selenides. It feels like a foundational blueprint. This controlled disorder principle, guided by these tiny liquid droplets, could fundamentally change how we engineer materials moving forward. For decades, like we said, materials science often chased perfection, crystalline order. But now we see the immense power of intentional, controlled imperfection.
A new way of thinking.
A whole new way. This new understanding opens up a vast, previously unexplored frontier in material design. So the final thought to leave you with is this. Consider, just for a moment, what other unnatural materials could we now potentially force into existence using the same principle? Materials that inherently resist forming thin films, maybe materials based on different elements entirely, or even structures we haven't conceived of creating at the atomic scale before.
Using liquid droplets to overcome their natural tendencies.
Exactly. Could this principle be applied to create completely different types of thin materials with tailored, unique properties? Perhaps in fields we haven't even touched on today, far beyond just electronics and energy. It really feels like it boosts the great potential for discovering a whole new generation of devices and applications we can barely even imagine yet.